Science on Surfaces.
Hello there and welcome to Science on Surfaces, Tips, Tricks and Tools. I am Marina Axelson-Fisk. In this podcast we want to share knowledge and inspiration related to life in science with the ambition to help facilitate work progression and simplify everyday life in the lab. In this episode we will talk about modeling and mathematical models in science. And here with me in this call I have Professor Marina Axelson-Fisk, Professor in Mathematical Statistics at Chalmers University of Technology. Welcome, Marina.
Thank you.
So this is the third time we have the honor of having you as a guest in this podcast. In episode 28, we talked about design of experiments, and in episode 31, we talked about data analysis basics and how to make the most of the collected data.
Yeah.
And both of those were very educational conversations. So to those of you out there who didn't listen to those yet, I could really recommend episode 28 and episode 31. It's fantastic you have so much knowledge that is relevant to our listeners, and it's fantastic that you're able to join us for another episode. So today we will talk about modeling. We briefly touched on that in episode 31 as well, but now we will dig a bit deeper. So we'll talk about what modeling is, some things that are important to keep in mind when modeling and so on. But let's start with the basics. What is a mathematical model and what is modeling?
Yeah, that's a good question. So this is very related to the other two pods as well, since data analysis and data science and design of experiments, underlying everything you do is a model. You have a model that you are assuming. So a mathematical or a model in general is an abstract representation of some real life object, say, and like a sculpture is a model of whatever it's portraying, or a painting is a model of a picture, and a mathematical model is just a similar thing but in formulas. So we're representing things in the real world with formulas. And typically you want to relate different factors or features or entities in the real world and see how they relate. So that's the brief explanation of a model. An abstract version of reality, relating different features in the reality. But so as such, it's of course a simplification of the real world.
And a mathematical model is then you're representing a phenomena or some process or something like that.
Yeah, so in the mathematical formula you have variables representing the features or entities that you want to measure, and then you have parameters that are constants that adjust how these variables relate to each other. So those are the typical formulations in a mathematical model.
So the variables is what you measure.
Yeah. So these are the unknowns that you want to understand more of and want to relate exactly.
And so when would you want to model them typically?
Yeah, so in science, often you want to determine the relationship between features. You want to understand how different features in the real world relates to each other. And it might be only because you want to understand more how things affect each other, or you may want to understand how different features interact with each other to make so their combination may have a different influence on whatever you measure compared to each of them separately. Or you may want to predict something, say that you want to predict something that is difficult to measure, but you have related entities that are easier to measure and that are connected, then you make a mathematical formulation how they connect to the thing you want to measure. This is very abstract. So say a simple thing is to predict the weather. You typically predict the weather by looking at the history, like the weather tomorrow is related in various ways to the weather today, and yeah, the experts, they use satellite pictures and so on. So they don't know the weather tomorrow, but they know a lot of other features that they can put in. So you may want to use the model to predict things or to classify things. So it can be used in many different ways. And in science, in applied science, it's usually you want to test relationships in various ways using hypothesis testing, for instance. And then you need a model first.
Okay. So I know there are different types of models, right? Could you just take us through a few? So I think, for example, there could be algebraic and evolution equations.
Yes.
I read somewhere.
Yeah, you caught me there. So I'm going to avoid the question a little bit like a politician. Yes, so there are many different models, and you can, of course, group them into different categories. And one important distinction is whether the model is linear or non-linear, for instance. When it's linear, it means that you can if you only have two variables that relate to each other, you can draw a line. And if you have more variables, then it becomes more complex. But that you have a linear relationships, meaning that if you have more than one feature affecting the outcome of something, they different features only add up. So you have the feature times a parameter, a constant, and then you add them up. So that's the linear relationship. While in a non-linear relationship, then you can have all kinds of messy functions. So you have like the exponential function, so e to the power of your variable, for instance, then all of a sudden you have a non-linear relationship. And why this is an important distinction is that well, I would say, first of all, linear relationships are much easier to handle, both to train the model and to interpret it. And in many applications, even though the relationship maybe isn't exactly linear, you can often get away with approximating a linear relationship. Yeah.
Would you have any examples of the two?
Well, yeah, regression is like linear regression then is a linear relationship, or did you mean like a real world?
Yeah, I'm thinking like a scenario that we could relate to. I mean, what phenomena could be described by a linear equation, for example?
Yeah. Well, I actually thought of my own master thesis, which I did for quite a while ago, where I was making a model for estimating the age of fetuses. So you have a pregnant woman that doesn't know exactly which week she's in, and then you want to estimate the age. And then I had a model that measured the what's the length of the leg, like what is it called, between the hip and the knee, the upper.
The femur. I think it's the
Yes,
femur.
the femur. Yes, thank you. And also the diameter of the skull.
Oh, okay.
So the way it was done was that we had a number of data points, number of fetuses where we knew the age and these measurements, and then we related that in a linear way to estimate the fetus age. So when there was a new a fetus or a new pregnant woman, then we just measured these things and could estimate the age. So that's an example of a linear relationship.
Okay. Yeah.
So non-linear relationship is I mean, it's anything complex. For instance, neural networks are non-linear relationships. So, and they apply very well to pictures, to images, photo pictures. So they can relate all the pixels in an image, and they don't have to add up linearly. They can have other complex relationships, for instance.
Okay. Yes, I have a list here of
Yeah. So that was one. Sorry, that was one distinction. So you have another grouping of models is between deterministic and stochastic, or random and non-random. So in a deterministic model, all your variables are set. They can be unknown, but typically the same input will always yield the same output. So it's a fixed or constant or relationship. While in stochastic models, you have some addition of randomness. You may have some noise in your measurements, or you have a distribution over your variables. So it's not a constant like the relation between blood pressure, say, and I don't know what that would relate to, but I don't know. I was about to say length, but that's of course not related. Well, there might be a relationship, but so there isn't this relationship may vary between objects a little bit, so it's not an exact relationship. Yeah, so that's the main distinction. And then instead of having measured variables just determined by the measurement, you also add on the randomness or the noise through a distribution of values. Yeah. And then maybe the third important distinction is whether the model is discrete or continuous, meaning if your variables are discrete or continuous.
So what you measure, if you measure something that happens continuously or discrete.
Yeah, so typically if you have a measurement device, you will get something that is continuous, meaning that you can get any value between any two values. There are still, depending on the decimal point and the number of decimals. While in a discrete, it's like you can count the values. You can count. You can separate the values and count them. They can be infinitely many still, but you would be able to count them. Yeah.
And so I guess in science, then there are probably already lots of defined models for various types of phenomena and scenarios and so on. But let's say you want to go about and create your own model because you're studying some new phenomena or some phenomenon that isn't so well studied or needs to be explored more. Then how would you go about then creating model for that?
Yeah, starting from scratch.
Yeah.
Well,
or maybe even just continue to work on something that exists but doesn't really describe the world in a good enough way, let's say. I don't know.
Yeah. So you first you need data. You need to have an idea of for instance, if you want to model a relationship, you need some data, and then you need to see how they relate in various ways, and that can be explored by visualizing your data, plotting in different ways to see. Then you would see, for instance, if it's a linear relationship or if you see other patterns in it. And well, it's difficult to start completely from scratch. You need to have some idea of what relations or phenomenon you're studying. So you need a lot of knowledge, and typically you would also survey the field. So you would look into what different methods there are and pros and cons with those. And you need to determine whether you want a deterministic or stochastic model, whether it should be linear or non-linear, or if it would work with a linear model. And also, you also need to think of every model is a simplification of the real world, but there is a trade-off between complexity and accuracy. The more complex your model is, the more accurate it is. But on the other hand, then it's much harder to handle. You for instance, need a lot of data to train it, and yeah, it's difficult to deal with. It's difficult to compute the results and so on. So you have to weigh the complexity towards the accuracy in some sense.
For example, I think for your thesis, when you said it ended up being a linear model, did you know from the start that it was going to be linear, or did you, because you created a model there, right?
Yeah, no. So there, my supervisor had the idea of doing this as a linear model. So we didn't really try anything else. But that's a good point. If you don't know, you should probably try a couple of different approaches, different models, if you don't know which would be the best fit. So that's one way to go about it. And of course, you can try to invent new ones by combining existing models. That's the kind of work I do a lot. I work typically on creating new models, and we rarely develop them from scratch, but use existing models and tweak them or combine from different parts and so on. So yeah.
So is that a trial and error approach that you use then, or how do you even adjust models? You have to have some sort of idea of, what changes to make or in an existing model.
Yeah. Well, it is. I wouldn't say just trial and error, but of course that's an important strategy. That's one of the strategies that you have in your toolbox, is to try different things. But then you perhaps need to give it some more thought. If you see that something doesn't fit, then you need to figure out why it doesn't fit. Try to understand. For instance, if you're doing a linear regression model where you have an output and then you have one or several input variables. If you have done it as a linear relationship, and then you can check whether this is a good assumption, and if it's not, then you might want to change a different way to adapt your function to your data. And maybe if you see that there seem to be dependencies between data, you need to take care of that, and maybe there are additional features that need to be included in the model and so on. So sure, it is often a kind of trial and error, but with some thought behind, that you try to understand why this doesn't fit. And then you try to benchmark it by testing on data where you know the answer, so to speak, and then you try to understand why it doesn't fit, basically. So yeah, it's not a clear, it's a vague instruction. Try, but do it smart.
Yeah.
But that's the fortunate thing with internet nowadays, that you can find so much information there, and also by being clever in what you search for, you can find new ideas, maybe things that are tried in a different but related field and so on. So reading a lot is a good advice.
So how do you, I mean, how do you know when to draw the line, so to say, in terms of improving a model? You said it's like a trade-off because you can make the model more and more complex, of course. But I mean, how do you know where to draw the line?
Yeah, that's difficult too, of course, because depending on what you're doing, you may, if possible, you may have that as an understanding already from the beginning, how close, how big variation can I accept? Because if you have a stochastic model, it's about how big variation the data is, and then if the variation is too big, you need to either have a better model or have a larger data set or and so on. And if you're training your model, meaning that you're estimating these parameters in front of the variables from data, if you do that iteratively, for instance, then you can either have a decision that you have some error function, say, that tells you how far from the truth you are when you train on annotated data. You can say that when I'm within this interval from that, then I'm done. Then my parameter estimates are good enough. Or when the error doesn't change between iterations, you have the same error. The error becomes constant or near constant. Then that would be a place to stop, possibly, because then doesn't matter how much you do, you cannot do it better. And if that's still not good enough, then you need to again review your data, your model. It relates to this design of experiments that we talked about in the previous pod, that you need to think things through and try to understand if there are variables that you cannot control, say, that still affect your output. Then you need to figure out if you can, or control, but variables that you cannot measure, but you can try different ways to control them by trying to keep things constant. For instance, if you have some model where you measure things, and for instance the temperature may matter, then you may try to measure under the same temperature every time under the same circumstances and so on. So there are many things to think of, and that you can tweak also, but that can also affect your results.
Yeah, and the parameters that you mentioned, how do you extract those? That's just by fitting data to the model,
You
and
mean
then you can.
how you estimate their values, or how you?
Yeah, exactly. How do you estimate their values? Yeah.
Yeah, so there are different methods for that depending on what model you're choosing. So yeah, so there are parameter estimation methods. Supervised learning is the machine learning name for it. So yeah, I cannot say directly which method you should use. There are in statistics, maximum likelihood is a method where you try to optimize the fit of the data to your given model. So the model typically gives what method or methods you could use. Then there are iterative approaches, like if you're training a neural network, you do it iteratively and you estimate the error, meaning the difference between the true answer and your current one. And yeah, so there are many methods for parameter estimation as well.
Let's see. Yeah, so I was thinking about validation, but we talked a bit about that in terms of validating the model, or you talked about in relation to the model improvement or model. I guess that relates to validation as well, right?
Yeah. But there are additional methods, again, depending on what you do. But if you're doing hypothesis testing, which is within my field, you typically have a lot of assumptions that need to be fulfilled. This model you're using, for instance, in a common t-test or also in linear regression, then you are assuming, or the model assumes, that your data is normally distributed and it is the sample points are independent, coming from the same normal distribution, and also that the variance is constant or near constant, so that you don't have a variation of variance, a variation of variation over a range, for instance. And there are different ways to check whether your assumptions are fulfilled, whether your data fulfills these assumptions. You can plot in different ways to see if this appears to be true, and if it's not true, there are also various ways to fix it. You can make it more linear. You can make it more normally distributed by various transformations, for instance. And there are also methods where you don't make these assumptions. So you need to understand, if you're using analysis methods, you need to understand what assumptions are done, because the computer program will not know, and it will not check whether the assumptions are fulfilled. It will only output what you ask of it.
Exactly. And I'm thinking it can be difficult probably sometimes to know if the assumptions are fulfilled. I mean, you need to have quite a bit of understanding of the system under study.
Yeah.
In order
And
to use them.
visualization is very good. It's a simple way of getting a good idea of your data, plotting in various ways, plotting the variation, plotting the data itself, and so on, to see if the patterns are as you expect them to be. But a caution there, you have to be careful. So because human beings are experts at finding patterns even when they're not there, so you need to be careful so that you're not seeing something that isn't there, or seeing something that is actually just local to this particular sample. So if you see a pattern that you didn't expect, then you need to draw a new sample and make sure that it's still there, basically. And so on.
Yeah. Yes, I'm thinking, I mean, how to, it's somewhat related as well, but how to relate, if you're studying a physical phenomena and you have a model, and then, I mean, I guess the weather is a good example. There is a model, and often I would say that the weather model is not perfect, at least not the model used here in Sweden. I mean, it's on the West Coast. I guess it's very difficult to predict the weather.
Yes.
In general.
I think so.
But when you have a model describing a physical phenomena, and just knowing that the model actually represents what you have there, and that the assumptions are correct, I guess you can't really use the approach that you just described, where you plot the data in different ways, or can you? Are there any ways to assess if the assumptions are fulfilled, so to say?
Well, yeah. There is no completely secure way to do this, a foolproof way, of course. But if you have access, or could get access to data where you, for instance, when you want to predict something, where you can, with weather data, you can go back and split the data in training data and test data, and then see if your model trained on the training data actually gives the prediction, because there you can see how far off you are, and if it doesn't fit, then you need to try to understand why. It can be, again, that your model isn't the correct one, or that you don't have enough variables in it, or something else. and this idea of splitting your data into training and test sets, it's called cross validation. And for whether you have a timeline, so there you need to split it like that. But in general, when you have a data set, a good approach is to split it in several ways. So you do a split in training and test, and then you do like a orthogonal split in training and test, and do this a number of times, or randomly split it, so that you get your validation from different points of view, and then you see if yeah, how well your model fits. And this can also be done to figure out which features are the most important ones, and if there are missing features and so on.
So in the previous episode we talked about softwares and tools to use, but I guess in this case you would have to use some sort of modeling software or data analysis tool that would help you, and I guess it depends also on what you're working on.
Yes, of course, but Python is coming strong. Python is a programming language, but it's becoming an overall tool where you get modules are developed all the time, and then you can download. So us in mathematics, we have used tools like MATLAB or R or Mathematica, and those are still, of course, good to use, but it seems like Python is about to take over entirely. So you don't have to use different tools. You can do everything in Python.
Is it also, I've never used it myself, is it also more user-friendly, or is it that it's more powerful, or that it can address aspects that the previous softwares couldn't?
I would say it's similar to using MATLAB or R. There you have to do some sort of programming as well, and Python is in many ways very similar to R. So it's not easier, but I would say it's not harder either. Yeah, and there are, as I say, many people develop tools in Python. So there are many times there are already existing modules that you kind of just need to understand how to plug in modules, meaning finished programming packages. But as long as you can do that, then you can. It's like using predetermined functions in MATLAB or R. There are such predefined modules in Python as well.
Okay, so why do you think a lot of people think this is difficult or challenging? Or at least that's my impression, that people find this difficult, modeling.
Yeah, I thought of that. Tried to prepare for this pod and thought of why is this so hard? And I think, well, this is a good question. I think it's the same reason to why many people find mathematics so hard. And I, of course, have a little bit difficulty to relate to this. But at the same time, as I am teaching mathematics, I need to understand why it's hard or what is hard. And I think one thing is that mathematics, as in many scientific fields, knowledge is really built on each other. So you need to know the building blocks in your theory, and if you are missing one block, the whole building may fall. So you need to know the steps, and as tedious as it may sound, you may need to go back propagate through your knowledge and see where the missing piece is if you don't understand something. And this is something I have to do regularly at myself, because of course I cannot know everything, and this is just part of the area of modeling, that you need to find new clues to why this is difficult. But so if you find it difficult, you should try to trace back to where your missing blocks are and try to understand them, because each block in itself, you can learn mathematics in small steps, so you can always improve a little bit. You may think that the gap is huge, but the missing block may actually be quite small. So yeah, I don't know if that explains why people find it hard, but it's also reputation of mathematics is that it is hard and that you're really smart if you know mathematics. And well, I wouldn't sign under that. sign off on that. I don't think I'm that that smart.
But so it's more of a general, like, mathematics barrier rather than a specific aspect of the modeling. So it's not like people are getting stuck somewhere. It's more of a general sort of fear, not fear of, but like a respect of mathematics as an area. You think? Yeah.
Yeah, and that you again that you need to trace back to where your lack of understanding is. So you need to be patient and you need to be brave, I would say, that if you feel stupid, try to get over that and just I'm trying to encourage my students to ask questions, and I say that, of course, that there are no stupid questions, and this always sounds like a cliche, but I have never encountered a stupid question during my career. Even if you ask, I don't understand, can you explain that again? That doesn't sound stupid to me at all. On the contrary, you're aware of your lack of understanding and you're doing something about it. So that's excellent if you ask that. And the funny thing is, I learned this myself, because when I was a student, I was also afraid to appear stupid. So I was careful. And then many years after, I spoke to a professor and he said, "Oh, I remember you in my class. You were really, really good." And his class, I remember, was the most difficult class I've been to. And I didn't understand anything, but I kept asking questions because I didn't understand. And what he remembered was that I was a very active student. So
Exactly.
if
Yeah.
you're afraid to appear stupid, then
Yeah.
you won't.
No, exactly. Yeah, that's a very good example. Yeah, I was thinking that, maybe people find it difficult to, or maybe they don't trust their ability to do the assessment of model validity, and, you have to make sure that the assumptions are fulfilled, or and also make sure that the outcome, is correct or true or whatever. And maybe it's difficult maybe to trust your ability to do those judgments, maybe.
Yeah.
That was one aspect I was thinking. And maybe, I don't know if that relates. I guess it's related to understanding and skill in some way, but it's also related to uncertainties and how to relate to uncertainties.
Yeah.
But science, that's science for you, I guess. Yeah.
Yeah, but of course, if your main area is not mathematics, but you're using it as a tool, I totally understand that it's difficult to be an expert at mathematics at the same time. So again, ask questions. Ask people that you know can answer this. Try to involve a consultant, for instance. There are statistical consultancies that you can speak to, or in a company, it's always a good idea to employ a statistician or mathematician, and so on. So ask for help. Then I know myself, it's difficult to find someone that has time for it. So it's but of course you're not expected to understand everything, but try to begin small and try to understand that little area where you're in and try to understand that model instead of thinking that you have to have all the mathematical theory behind you.
Yeah, but that's great advice. Ask questions, and there are no stupid questions. So when I'm thinking what's important to consider when modeling, we already touched on a few aspects. We talked about the assumptions and needs to be fulfilled. Anything
Well,
else?
you need to understand the problem that you are trying to solve. You have to have good knowledge of the data that you're dealing with and what relationships you want to model, and of course some of the basics of what types of model can be applied. And you should also think of keeping things simple. Start with a simple model and build up rather than throwing in the most complex deep neural network that you can find. There you of course you can do that. I'm not saying you shouldn't, because there you don't have that many assumptions that need to be fulfilled. But I notice also that there's a fashion in what models to use, and so deep neural networks are very fashionable. And I see when I supervise master thesis students now that everyone wants to work on neural networks, and I understand because I think they're really cool, but they're not suitable for every problem. On the contrary, they are very good at certain things and quite bad at other things. So you need to get an understanding of what group of models that work best for your particular problem. And in order to be able to choose that, you need to understand the problem properly first. And yeah.
So what are the challenges and pitfalls to avoid in general? Are there any that we
Yeah,
could
so
list?
this, well, it is this, what I've said, try to keep things simple. Don't use models automatically without reflecting over what they mean and what assumptions they require. Make sure that you know enough about your problem. Be skeptical with your own results so that you avoid your own tendency of searching patterns. Of course, that is what we're trying to do, but to avoid falling into the pitfall of finding a pattern that it is not there. Be very, very, very skeptical and try to disprove your own thesis. Try to find other explanations to why this might be, and so on. And always expect issues with data. Don't think that this will be smooth. Just expect that it's not going to be. There are always, when you are dealing with real data, that it becomes dirty. So be aware of that and try to be prepared for that. And be very patient and curious are the key ingredients, I think.
Yeah, exactly. I think the expectation is that probably data analysis, but also modeling, all this kind of data treatment, that it will always go smoothly. And that's not my experience at all.
No, mine neither. Real data is a pain.
Yeah. So just keep that in mind. Anything else that we should add? Any advice to someone
I think
who?
we've covered what I would suggest. And don't think you're stupid.
Yeah. Yeah. That's a good starting point. So yeah, so I think we've covered the basics then of modeling.
Yeah, very abstract. I realize it doesn't give you. It would be nice to have a recipe saying, oh, you do this and this and this and this. And unfortunately, the field is too big to do that. But when you have particular areas of applications, you can well, a good start is to survey the publications in that area. Then you know how people have approached it. If you want somewhere to start.
Exactly. But I think also we could emphasize what you mentioned there, like knowing your problem. I mean, you have to have some quite good understanding to start with, and then you can move from there. Like you said, search publications and see what models others have used and so on.
Yeah.
So
And
that's
try
good.
to find communities to brainstorm in. I mean, talking to people, even if you don't explicitly hire a consultancy, there are many fora on the internet where you can chat and ask for questions and so on. So try to discuss your ideas or thoughts with people. I understand that sometimes it's if it's you're in a company or doing important research that you don't want to reveal what you're doing, but there are still many things you can discuss without revealing your latest brilliant idea.
Yeah, sure. So so we'll end this episode with that comment. So thank you so much for sharing your knowledge, or some of your knowledge, on this vast area of modeling.
Yeah.
And to all of you out there, thanks for listening to this episode with me, Marina Axelson, and Marina Axelson-Fisk, Chalmers University of Technology. And I would also like to take the opportunity to mention to those of you who are listening or watching that if you're interested in surface and interface science or related topics, you should check out our blog, the Surface Science blog. Thank you.